Before we move on to SQL injection, how can a stack be manipulated? The first and easiest attack scenario can rely on inserting a payload directly in the argument of a called function. Assume that an FTP server that we mentioned is vulnerable to buffer overflow. We check this by submitting increasingly longer strings as login and password. At some stage, the server failed. This is visible because we analyze it via a debugger. This means that an insertion point is found. An insertion point is a place where bounds checking an input value for length, is not being applied. How can the address of a return function be located now? Find an opcode table for the targeted software. It will contain memory addresses for system registers for the program. The next step is preparing a payload. It should be short and compact enough to be able to be transferred as a function call parameter. The final point is padding the payload with an ops slide. This will increase the likelihood of the victim's computer executing your code in the program you aim to control. It's up to you entirely to choose what your code will do. What is the danger related to this attack? Attack services, above all, have a higher level of permissions than the permissions of a user who runs an attack. It's no use applying complex techniques to control the execution of a program you run, since the program will have your level of permissions. System services usually run with escalated permissions that a user doesn't have. They, for example, run on remote machines. This is often locally reasonable because programs perform some operations with escalated permissions. If we were to seize control over this service, this would make us in fact the administrator of the computer. Let's now look into SQL query manipulation. SQL, unlike C and C++ languages, is interpretive. There's no compiled code and no compilers. The languages use interpreters instead. Interpreters are programs that translate strings. If an analyzed string is well-formed, which means it conforms to the version of the SQL standard that a given database server supports, the server will execute it. The source of the code is irrelevant. Many applications allow user input. Examples of this practice are logging forms that require a user to submit login and password to log in. You can't ensure that a potential attacker will not submit any other value to the form. The form will accept any strings. SQL statements in particular can be entered as well. The simplest case can include entering an expression that's always true. For example, OR1 equals 1. A more sophisticated option could be OR1 less than 2. If an application is susceptible to this threat, it will forward the submitted string to a database server where it will be executed. The string will be executed with the same permissions as the permissions of the application that connects to the server. If the application connects to a database server as the server's administrator, which is a widespread practice and makes SQL injection a significant threat, this means the code will certainly be executed provided it's well-formed. An administrator is able to run any instructions on his server. The second factor that aggravates SQL injection threat is the fact that developers or programmers often join SQL statements fragments with user input. They join strings. For a database server, the difference between the part of the string that is embedded in the application code and the part that is supplied as a parameter, for example, a username, is indistinguishable. The server executes all statements. Contrary to popular belief, the location of the string concatenation, whether it's on the side of the client application or on the side of the database server via stored procedures, does not alter threat level at all. We'll see this in a moment. The first part of this presentation will cover some basic techniques for manipulating SQL queries. We'll check if we can really manage to log into a poorly written application and then examine the possibilities of more sophisticated SQL injection techniques. Let's imagine typical circumstances for an attack. An application is poorly designed at first glance. Usernames and corresponding passwords are stored in tables in a database. They're in plain text. Regardless of what's contained in the database, anyone can access it. The usage of inbuilt authentication mechanisms for a used environment, ASP.NET or PHP, would be preferable. In any case, what we have here is a simple table containing a username, a user's password, and information on the user's status, whether or not he or she is a system or an application administrator. We'll enter 2 users into this table. In the system version we work with, we'll have to do this row by row. First, we insert the data of the first user and then the data of the other user. In a moment, a logging form will be visible. The form leads to an application that is prepared in this way, the altered database. A client application checks if the values submitted to the login and password fields match the ones in the rows in the table. How is this done? The simplest and the most dangerous solution is to execute the query given. This will read all the table rows that contain usernames and passwords that match the values we submitted. Why is this method so dangerous? It's because you can enter an always true expression instead of a valid login or password string. One characteristic feature of an alteration, the OR operator, is that if one operand is true, the other's value is practically irrelevant. The result will always be true. Since the next part is a code fragment that checks passwords, we don't want to execute. What should we do then? We need to mark the latter part of the string, the commands at the right side, as comments. To include inline comments in SQL, use double dashes. Let's check this solution. Without submitting a username or a password, we're able to read all contents of the table.